Yeah. So we said in this new chapter, we're going to take it a step further because we are almost close to the end of the chapter. We, the purpose of this chapter was for us to create tokens and then embed them. We are very close to embedding those tokens, but there's one more concept that we need to discuss before we talk about embedding these tokens, and that is data sampling. We're going to talk about data sampling and sliding windows. Sliding windows. So these two concepts would wrap up part of our tokenization and getting our data in before we can embed it. So let's see what that means. What we know about large language models is they do next word prediction. Next word prediction. That's how they are trained, right? They're trained to do next word prediction. So for example, let's say we have this text sample. So this is going to be our text sample that says this, and I'm going to use different colors to highlight a point. So let's say they say LLMs and then learn. Let me see if I've a color that is slightly different. Just going to set up, I'm trying to set up a color that is slightly different here. Okay, think that should work. Yeah, so that one, yeah. LLMs learn to predict one word at a time. That's what we have, right? And then in the next iteration, it will say, this is now the input text. LLM learns, and then what it's supposed to predict, it is this two. Predict one word at a time. And then in the next iteration, it will say LLMs. Oh, it's supposed to be LLMs learn, not learns. Sorry for the bad English there. LLMs learn, and then two is now in the input text. The new predicted word that's supposed to be predicted is predict in this iteration here. And the reason why I am using this grayish color, brown grayish, is because large language models, they do not see these words one word at a time. The LLM itself can only see these words that have been here before. These are the words. The LLM can only see these words to try predict this one here. So as the sequences go, as the iterations go, first iteration it's predicting learn. It doesn't know that that these are the words that it's going to predict in the future. It doesn't know that. It only knows LLMs learn and then LLMs and then it predicts learn. In the second iteration, it knows LLMs learn and then it predicts two. And then the third iteration here, it knows LLMs learn to, and then it predicts predict. Going on and on and on and on like that. It was given a text sample. What we need to do is we need to extract blocks that we're going to use as inputs, which are subsamples that serve as the input to the LLM, and the LLM's prediction task is to predict the next word that follows that input block, like we have seen here. There's this nice block that is coming up here, and these are the predictions that it is making after each and every iteration. During the training, what we're going to do is, although here I put them as gray, the actual data set that we have, this is the full data set that we have. This is the full sample text that we have. This is the full sample text in the novel or in the books or everywhere. We actually have access to the full sample text, but when we are training, we are not going to give the model access to all the words at once. What we are going to do is we are going to use something called masking. So here we will mask out the words that are past the target at that particular iteration. So that is why these were gray. They were grayed out because at this first iteration, this is the this learn, it is the target. So we masked everything after the target. So everything here was masked from the LLM. It does not even see this. In the second iteration, 2 was the target. So we masked everything after 2. In the third iteration, did I say third in the previous? I hope I said second. In the third iteration, this predict was the target. So we masked everything after that target. So that's what we are going to do in this course when we're doing our data sampling. So if we are going to do it in code, here I'm now going to talk about something in PyTorch called data loaders. I'm really not going to get into the nitty-gritty details of it, but it's essentially a way to efficiently load data. Efficiently load data. If you've done neural networks, when if you've done like image classification or object identification and all of that, you might have 10,000 or thousands and thousands of images. To efficiently load them, we can't it'll be difficult to load them in like a for loop for each image and all of that. You can create what are called data loaders. Data loaders will create these objects where you have access to functions like next function. If you want to load based on your definition of the data loader, you could have batched, like we said, we might have 10,000, and you have batched them into 1,000. And this is the definition of a data loader. A data loader is saying batch 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 all the text that I have into 10,000, into 10 batches of 10,000 each. So what you do, if you say next, it will then move on to the next batch and the next batch and all of that. If you are using a batch size of 1, you have 10,000. So when you say next, it will get the next sequence and all of that. They are much more efficient. You can read up on data loaders, but they're much more efficient. And that's what we are going to use now to fetch the input, to fetch our input target pairs. And with our data loaders well defined, we can do the masking as well inside the data loader so that you don't have to recalculate the mask every single time manually and all of that. You just do it automatically. Um, so that's what we're going to do. And we're also going to use what is called a sliding window approach. So what sliding window approach does, okay, let me just write sliding window. So the way we are going to do a sliding window approach in a very intuitive manner is we're going to create the input and target pairs for the next word prediction by creating two variables, x and y. The x variable, it contains all the input tokens, and the y will contain the targets, just contain the targets, which are inputs shifted by 1. So here we just shift x by 1. That's the most intuitive, the easiest way we are going to create targets. Let's see how that's going to work. Let me switch to Python and we can see the data loaders and everything working now. Okay, so here we have loaded our verdict, loaded the verdict.txt book here. We have tokenized it. We have tokenized here. And so now what we are going to do is let's just look at a sample. And one thing I'm going to, so if you run that, it will just, I'm not going to run it because I'm not connected to the GPU, but you can just run this and you see the encoded text, the first, you see some, not the first, but some of the, yeah, I actually wanted to put 50 on this side so that you see the first 50 tokens, but yeah. because yeah, it's going to print everything else. So maybe I can just update this before sending out the codes to 50 to 49 actually, because Python starts at 0. So this would be the first 50. Here I'm talking about something called context size. So context size, it determines how many tokens are included in the input. That's all it says. How many tokens are we going to include in the input? Because here we have all our tokens encoded. I think you can see, for example, these ones are encoded like that. If we have context size of 4, we're just pretty much saying 1, 2, 3, 4. Those are the tokens that we're going to include in the input. That is going to be our X. And then we move on to the next and all of that. So we are going to create an efficient data loader. So for example, here, when I'm just encoding, context size is equal to 4, which means a sample. Let's take a sample. X it will just be this context size. So it will start at index 0, 1, 2, 3. These are the index 0, 1, 2, 3. If I had, you get a different answer, because this sample, when I did it, it was 50 going forward, which was a mistake. I just wanted it to be up to 50. So you get a bit of different answer here, but I can keep it. I can keep it because we are not really printing it out. So this is saying from like 50 going forward. So now let's see. So that X, this is now 1, 2, 3, 4 because of our context size. And we are going, and for our Y, we are saying we are shifting it by 1. So shift by 1 of our we were shifting our encoding sample by 1. So it'll be from from index 1, because yeah, it's starting at index 0, 0 to the 0 to 4. So this one here, it's actually doing something like this. Let me just put in it's 0 to 4. And so with Python it will be 0, 1, 2, 3, because 0, 4 it's like -1, right? And then here it's now saying, okay, I'm going to shift by 1. So it's going to say 1 all the way up to context size plus 1. So context size plus 1, 5. So it's going to include tokens that are in position 1, 2, 3, 4. So that's what Y is now. So X is going to be 290, 420, 920, 2241, and then 287. And then for Y we shifted by 1. So we are now getting 4920, 2241, 287, and then we have added a new one, which is 257. We have essentially just shifted by 1 to create our Y. So if I'm to go back our to go back to smooth draw, so I can just show an example. So to just have an example here, imagine that our sample text was something like this. Let me write. Imagine our sample text was in the heart of the city stood the old library, a relic from a bygone era. Um, yeah, I think I can keep. I can stop there. Okay, so this is our sample text, right? So when we are creating our X, those are going to be PyTorch tensors. These models, most of them, the ones I know at least, are trained using PyTorch. Um, so they're going to be Python tensors. So how do we create our X? So to create our tensor, or just think of a tensor as a multi-dimensional array. So to create our input tensor, X will be equal to a tensor or a multi-dimensional array. The first the first the first input text, it will contain these tokens. Of course, it will not be words, it will be numbers, but it will be because our context window, our context window is equal to 4. That's our context window, right? Context window is equal to 4. So we're going to have four tokens in each input. So that's going to be in the heart of. That is going to be our first input, in the heart of. That is our first input. And then our second input is going to be the city, and I'm going to explain what's going on. Some the city stood there. Yeah, there's a concept that I've skipped, and I'll explain it. I'll explain it. I can explain it now and come back to it later. Stride is equal to 4. So when we are getting stride, just means from one input to another, how many tokens are you skipping? Pretty much in simple terms. So from one input to another, how many are you skipping? Here we have context window equal to 4. And if our stride is equal to 4, it just means you're not repeating. So the first part, it will be in the heart of the city. That is input number 1. The second part will be this. The second input will be stood there, and then the third input will be this, because the stride is saying skip 4. For illustration, you can do stride equal to 1. And so the first one will be in the heart of the city. And then because stride equal to 1, you have the heart of the, no, the first one will be in the heart of. And then if stride equal to 1, you will now have the heart of the. And then the third one will be heart of the city, and all of that. We are going to discuss stride just towards the end of this video, but I guess I hope you see what I'm trying to explain there. So here we're using stride equal to 4, and so the third input is old library, then a comma, then the last one will be a. And so on and so on and so on until the end of until the last one and the end of the multidimensional input array. So this is the input array that we have, and our y is going to be a tensor with the targets. So this tensor with the targets, it's going to be derived from the same simple text, but we said shifted by 1. Shifted by 1. So y is a tensor, also multidimensional, but shifted by 1. So which means y starts on the heart, the heart of the. So this is the first target, the first y. Then because of stride equal to 4, it skips as well, and then it jumps to city. City stood the old, and then stride equal to 4 skips 4, jumps to library, comma, a relic. I hope you can see that y is really just x shifted by 1. X shifted by 1. And it continues as well, all the way up to the last one. All the way up to the last one. So we can see that each row in this input tensor represents one input context. One input context for each row here. Y contains the corresponding prediction targets, the next words, which are created by just shifting by one position. So in our code, we are going to now create the data loader GPT, we are just going to call it GPT data set, and we are going to use the V1 because we are going to play around with some of the parameters there, but we're going to say that GPT dataset V1 that loads our dataset, loads our text from our text file, creates these XY inputs, observing the context, context width and the strides and everything, anything that we want to put there. But at the end, we hope that it gives us our X and Y. Uh, so let's actually look at the code and see where that is happening. Okay, so we can switch. So now this here is just showing you how you can do using a for loop using so our when it's 210, we said when it's 210 our prediction is going to be 4920 like we showed. When it's then we add the 4920 into the input array, right? For iteration. Then our prediction is supposed to be is now 2241. Then we add the 2241 into the array, and our prediction is now 287. Then we add that in the array, and our prediction is 257. We want to here it's just the words themselves and established, but we want to do that using a better way. Instead of using a for loop, we're going to use this data loader. So it inherits this data set, which is the data loader, which is it inherits the data set and data loader from PyTorch, so that we can extract the chunks from the input text. So here we are creating our input IDs and our target IDs. We get the token IDs, and we allow special. So the encoder from tick token will tell the encoder from tick token that we are allowing this special character called end of text. It's coming from GPT, right? You remember that tokenizer coming from GPT-2 tokenizer. So it uses the this end of text character if we allow it. So those are the allowed special characters. We can put some more, but that's just the one that we want. And then we're going to use that sliding window here. Using that sliding window to create our input targets and our input IDs and our target IDs. You can read the code there, that for loop that's happening there, but it's pretty much what we explained, where we are sliding, where we're sliding by the stride that we're going to use. Whatever stride we're going to use that to 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 create our inputs. If it's stride of one, we just move the input window by one. But if it's stride of four, which is equal to the context length or the maximum length, then it jumps in blocks, just like we explained. That's pretty much what it's doing. And then yeah, so we create our data loader there. We just created our class. This is the data loader where we're creating it, and here we're using a batch size of 4. Batch size of 4. The batch size is we have 10,000. We have 10,000 inputs. We have 10,000 inputs. We are dividing them into batch size of 4, into batches of 4 each. So which means our input, it will be blocks of 4 each. That's pretty much what the batch size will be. So in case, let's say we have 40 samples. We have 40 samples. If each batch size is 4, it means we have what, 10 batches. We have 10 batches. Then we are going to use a maximum length of 256. So this maximum length of 256 is our context window. Although our context window back in our examples was 4, that was just for illustration purposes because it was difficult to really show 256 tokens on a when I'm writing on a whiteboard. The context length of 4 was just showing you how the text is split into 4 tokens. But in practicality, we rarely use 4. We usually use 256 going upwards. And more powerful models now use way more tokens than 256. This is just for it to be easy for us to compute. So now 256, that's the one that we're going to use, and a stride of 128, which means there's going to be a bit of an overlap because our context window is 256, but our stride is 128, which means one half of that context of an input context will be carried forward to the next input. I hope you can see. I hope you can see what I'm trying to explain there. Okay, if you can't see, let me because it might be difficult. Let's just switch back to smooth draw so I can show. Again, re-emphasize. So if we have our context window that we are working with is 256. So which means here we have 256 numbers or tokens, right? We have 256 tokens. So if our stride, so here it will be 256 tokens. If our slide, and then there will be the next input, then there will be the next input, then there will be the. So actually, this is if it's our text will belong like this, and then we will cut it 256. We cut it, right? We cut, and then we create our input number one. That's input number one. And then and then the model and then our data loader will then say, but what is the stride we are using? It will check the stride. If we had used a stride of 256, it was going to skip 256 and then create input number two here. But because we are using 128 as the stride, it's going to say, okay, 128, I'm going to go to 128, which is the half portion, and then it will create the second input like this. So which means there's a bit of an overlap here, bit of an overlap. So some tokens are going to be in input one and input two as well. There are advantages and disadvantages to that. We'll briefly touch on them later. But yeah, that is what is happening with our 256 there. So we can quickly switch back to our code. Cool. So that is what is happening. And then shuffle drop last equal to true number of workers that are going to be there to just make it to parallelize everything. So then we initialize, we load our data, we create the data set, and then we create our data loader. Our data loader is going to be from this data set, the data set which is just the text that we have using this tokenizer with this maximum length that we have and the stride that we're going to use. You can read the class what it's doing there. And then this is our data loader. This is our batch size that we're going to use. Cool. Return data loader. So now we have our data loader. You can read up on the data loader, but it's just an efficient, much more efficient way of loading your data. So let's test this data loader by giving it this txt. Now that we have our raw text, we then say data loader, create a data loader, because a data loader will come with certain functionality like dot next. So that's what we read. That's why we really want our data loader, because it's much more efficient for us to deal with these inputs and outputs. So we give it the raw text. Here we're just using a batch size of one. Batch size of one. We are back to our using our max because we are overriding. This is just for us to test. We are overriding our 256 and our stride of one. That's for us to just play around. So just to see the results, to see if it's working, we see that our our first batch. So you see our data loader says iterate. So it iterates over all the inputs of context one, iterates over the inputs of context one with strides of one. So now when I say first batch, I want to know the first batch. The first batch here, it's going to be data we're going to say next. It's just going to be 40. If you want, you can actually you can look at the tokens that are there in our raw text. When you tokenize them, you see that they are also the first will be 40, 356, 2885, 114. That is our first batch. And then the y associated with that first batch, because here we are returning the input according to our class. We are returning the input IDs, the input token IDs, and the target token IDs. And the target token IDs have been shifted by one from our shift. It's our inputs shifted by one, right? So 4356, those are our inputs. And then this is our target, 356,285 with an additional 187. That was now at the end. And then the beauty of a data loader, this is the beauty you see. For us to get the second batch, we don't have to do any calculations around. We don't have to do those calculations. Just it will do it by themselves because it is already loaded. And we just say next. What is next? What is the next batch? The next batch is because we are using a stride of one. It is now just saying, okay, the next input I'm striding by one. I'm just going to move to one to the next one. That is why 356 is coming out as the first one. If we were the stride of equal to maximum length, we would have had different numbers to this because it would have jumped to the next four, to the next four, but we do not have that right now. We use the stride of one. You can actually, when you get the code, play around here and put the stride of four. You see that the numbers will be different. But in this case, stride of one, the 356 becomes the first one and 187. And again, for us to create our target, we just shift our input at that particular batch by one. So it's going to be 256 and all of that. I hope the ones are not confusing you because the stride is one, and then the shifting of the input to the text is also one. I hope it's not confusing. If you're confused, just play around with this batch to see how different it is. The target here, it will always be one in this case here. It's always equal to one, where we are shifting to say, because what we're trying to do is next word prediction. So the next word is just plus one from the input that we have. So that's why it will always be one here. We can show, yeah, we can actually do when we're doing a stride of four. Like I'm saying, you can do stride of four and that will give you a totally different input. um so let's now see if we, I think maybe that is because many people get confused with the stride. So maybe let me get back here and re-emphasize that part of stride. So now imagine we have another sample text so that we can put some words down. Imagine we have this sample text here. um in the heart of the city stood the old library, stood the old library, a relic, a relic, blah, 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 blah. So that is the text that we have. So if we, let's see the effect of stride. So the effect of stride is if we are using, we are doing batch one. What is the input for batch one? Input batch one is going to be context window. Context window is 4. So it's going to collect these in the heart of, that is batch one, right? The input for batch one would be in the heart of happy. So if we have stride, if stride is equal to 1, here we're not talking about the y, because the y will be plus 1 of this input. It would be the heart of the, we know that for this particular batch, that is going to be the y, doesn't change. But if we have so if we have a stride of 1 to create the next input, so stride affects input. If we are going to say stride is equal to 1, batch 2, batch 2 will now be created from here. It will just simply shift by 1 or skip 1. And then it will say the heart of the. So that becomes the new input. And you can see there's an overlap with the heart of, the heart of. That is the overlap that we have. So stride of 1 moves the input field by 1 position. I'm going to use orange now just to, if we now change our stride, stride is equal to 4. If we change our stride equal to 4, our input batch 1, it will say the same thing. In the heart of happiness. That's how it will say. In the heart of input batch 2. But because our stride is equal to 4, our first input batch was this. But because our stride is equal to 4, The data loader is going to say, okay, you want me to skip four? 1, 2, 3, 4. I'm going to skip this four. So I'm starting here now. This is now your second batch. So the second batch becomes the city of the city stood there. And so this is tried equal to 4. There again, the y will always be the same. The y will always be the same no matter the stride. So here the y was always going to be for input batch 1, the y was going to be the heart of the, and for the second batch it was going to be heart of the city. Stride equal to 1. Also for when stride equal to 4, it will say in the heart of, the y was going to be the heart of the, because we are moving plus one on the input, plus one on this input. We are saying we are starting at city. City stood the old. So this will always be plus one. This will always be, to get this, we always add plus one. No matter the stride, we are just saying plus one. Because what we're trying to do is next word prediction. That's what we're trying to do. We're trying to do next word prediction. So we always do the next word plus one to get our y. These are our y's. Y's are not affected by stride. I hope I've explained that well, because many people are confused. They get confused when we talk about when stride is mentioned and all of that. It's like, oh, but stride, how is it affected? Stride affects the input, and the input will be the target will be plus one. So here now let's look at our data loader. We've said it's going to be a batch size of 8, which means each input is composed of 8 texts. Each input is going to be composed of 8 texts, and then we put it in a batch on the side. We create another input block of 8 on the side, and each input length, we have 4 tokens. We have 4 tokens. So this just says we are going to group our inputs into 8. And each one of those that are in each group of 8 will be 4. And the stride just says, how are they being created? We are creating by skipping 4 tokens every time when we extract the when we extract. So yeah, it'll go into our text, and then it'll say, oh, okay, cool. Max length, what are the first 4 tokens? First 4 tokens, it puts it on the side. As these are the first, puts it on the side. Puts it into this box, right? Puts it on the side. And then it counts 1. In that box, we have 1. And then it goes, it'll be like, oh, but you want me a stride of 4. Okay, so let me skip the first 4 that I already have so that there's no overlap. I'm going to go to the next 4. He gets the next 4. And then gets the next 4, gets the next 4, until he gets to 8. And then it says, this group is done. So this is the first input. That group is done. Let me park it on the side. He parks it on the side. And then he packs it along with its targets. Its targets are always plus 1 for each input. So you see, input number 1, this is input number 1. It will be, this is going to be the target for input number 1. And you can see the 187 has now been added here because we just shifted to create the target, we shifted by 1. And then for input number 2, when we skipped the whole thing to go all the way to number 5, starting at number 5, we created our input, and this is the respective target, which is just plus 1 of that respective of that respective input. That's pretty much what's going on here. I hope you can actually see these numbers and how they are working. But yeah, so now we have our inputs and targets, and we just use next, which means it spits out the next one. So we're going to spit everything. What then this data loader, what it allows us to do is, when we are training our model, you can train it batch by batch, because we can train the model on this batch of inputs and its corresponding targets, calculate our losses or whatever it is, calculate our error matrix, and then move on to the next batch with our next. The next, we'll move on to the next batch, next batch, because batching will allow us to save on memory and all of that. It saves on many things, especially when your batch size is not like equal to 1. If it's equal to 1, it's going to do like one input text at a time, it's going to be very noisy in your metrics because it might jump up, the error it might jump down, it might jump up, it might jump down. So that's where the art of data science comes in. You play around with some of these numbers here, to really get the optimal number that will train your model properly so it converges in good time. You don't want it to be training for months and months, you want it to converge in a reasonable time, but you don't want it to be too noisy at the same time. And there's no fast rule, but yeah. So that's what I wanted to emphasize here. And as you can see at the bottom there, they are token embeddings, which is the core of what we're trying to do in this course. So let's just close off the course with the token embeddings, and wrap everything up. So I'll see you in the next video.